Okay, let's resume our program of foundation engineering. Today, we will complete this first chapter at last. Okay, and then maybe this program will become more interesting. Okay, so we will still do on this before last point, the common method used for modeling yielding behavior of soil, and then we just add one additional example, and that will be the end of this first chapter. The example will be on the CAM-clay, modified CAM-clay model, how to determine the parameters needed that are needed for the modified CAM-clay model in numerical analysis. Okay, so here is another new model, new, I will say, stress-strain relationship that is used for numerical formulation, numerical modeling. Okay, the concept of stress-dilatancy theory for granular soil. This is only for granular soil, not for like cohesive soil, not for clay. Okay, for this stress-dilatancy theory developed by this reference, okay, is result of research conducted toward understanding the deformation of soil as a discrete particulate matter. Okay, the following assumption form the framework of this theory. This theory is using this following assumption. The first assumption is during deformation of the soil, the soil particle are tending to slide instead of rolling, and that is actually true. Okay, so soil particles tend to slide much more frequently than rolling. The second assumption is that the individual particles are rigid and they cannot contribute to elastic component to our deformation. The last assumption is that instant sliding is confined to some preferred angle. So it means the sliding direction is going in a preferable angle. Okay, so the following assumption also can be used to describe the strain. As I said, as we say, this is the equation that is giving the relationship between stress and strain. This concept of stress dilatancy theory. Okay, so this, you can see this equation. This is like a ratio of the principal stresses, sigma 1, sigma 3. Okay, in this equation, this angle CV, the phi CV, is the angle of friction under large shearing strain, where the shearing would occur under constant volume. And this ratio, as I was saying, ratio of principal stresses, stress ratio, it is under triaxial condition, sigma 1 over sigma 3 can be related to the developed angle of friction. The angle of friction that is developed during the shearing. And we can link it like this. As you can see, the difference between this equation 76 and this one is just this matrix. The only difference is this one. Okay, it means this one is 1 in this case. And in that case, this critical, or let's say this angle of friction under large sharing become just phi, normal phi. Okay, so I think we will come back later on this also. The rate of volume change, the rate of volume change, which is shown here. Okay, dv d. Actually, this is just sharing, the sharing strain. Okay, volume change and sharing strain. So this rate of volume change with respect to the share strain at a constant confined pressure, which is this ratio, can be expressed in terms of dilation angle. Okay, so we can say that this, we can use correspondence between this ratio and the dilation angle. The dilation angle is just this one. Okay, so this ratio is equal to the minus sinus of the dilation angle. I hope you people understand what is dilation angle. So I will put these two equations here. So this equation 75, this one, okay, is showing that when the sharing is occurring in the granular soil without any volumetric strain is, I told you, related to this one. So if there is no volumetric strain, it means this one is 0 and this one is 0. And we will have 1/1 here. All this part will become 1. And in that case, this angle, phi CV, will become just phi. And we will have these two equations will be the same that time. Okay. On the other hand, on the contrary to this one, when instead of this theory, in the case of dense or medium dense sand, the shear failure will occur at the maximum dilation, dilation condition, which is shown in this figure. So here is when we have granular soil and when the sharing is happening without only any volumetric change, no volumetric strain, actually, no volumetric deformation. Here we have dense or medium dense sand, and the failure is happening when we are at the maximum dilation condition. You see the dilation sin V, this dilation angle here. See? So under this condition, the developed angle of friction will be same as the angle of interparticle friction angle. This one, interparticle friction angle. So in that case, we can replace this one by this one without any problem. And this condition will also correspond to the occurrence of the maximum principal stress ratio. This means maximum value of this sigma prime 1 over sigma prime 3 in this case here, same. Okay, this is for medium dense and dense sand. But anyway, the most important thing is just this one. So this is what we have to give the software and to obtain the deformation that will be generated by the load. So this the same equation is also can be fixed, can be modified, arranged to fit the D matrix. Do you remember the D matrix in the finite element formulation in the section 180? Okay, so this matrix will then provide a mechanism to correspond plastic deformation of granular soil in finite element modeling of a foundation problem. And this is just a reminder of the D matrix, what I was talking about. We did this several times now. This is just an example of D matrix. Okay, so we can modify this to fit a D matrix like this and get a proper relationship between stress and strain. Okay, we will now move to the this one. One example to finish this chapter. So for this yield function, the numerical modeling, this previous section of this chapter, I think it's important for you to understand the CAP model and the modified CAM clay model. The modified CAM clay model is for clay, and the CAP model can cover large range of soil. Okay, so that's why in this example we will talk about the CAM clay, modified CAM clay model. This is an example considering a normally consolidated clay sample, which is taken from at 2.5 meter in an embankment. Okay, and then after taking the sample, a triaxial test were performed. Okay, undrained triaxial test and consolidation test to get soil parameters. Okay, in a lab test. Okay, so we got the more column friction angle here is 20 degrees. I hope you understand what is this, but if you don't understand, don't worry, we will come back on this. And the slope of isotropic consolidation line. Okay, if we do this consolidation test, do you remember the apparatus for consolidation test? If you go back in the previous video, you will see that we have talked about this consolidation test. Okay, please remember that we may have two lines, this line and a line like this. We will show a figure talking describing this. This first line, the isotropic consolidation line, the slope is 0.3, and the recompression line, the slope of isotropic recompression line is 0.05. Okay, so two lines, this one and this one. Using consolidation test, you can get this line. Okay, so the thing is, we want to use maybe modified CAM clay model to use to in numerical analysis. Okay, from the soil parameters obtained from this soil sample. So in that case, we have to estimate the modified CAM clay model parameters. Okay, we have to calculate them, estimate them. And then the second question, we are asked to, by assuming that the void ratio is 0.9, to develop the relationship between stress strain, okay, stress strain relationship to be used in a finite element model. Okay, we get the relationship is just the equation we provide last time as equation for modified CAM clay model, okay, to predict deformation. So this is all, this slide is just a reminder. Okay, this is the relationship, actually, stress strain relationship for modified CAM clay model. Okay, and these are the soil parameter and the associated lab test that are necessary to obtain these soil parameter. Okay, isotropic consolidation and a triaxial test. Okay, so these are the parameter for calibration. So what we want to do here in this example is to obtain all these parameters, this lambda, this kappa, this v, p, m, all of them. Okay, we want to obtain the parameters of this D matrix. If we obtain this D matrix, then we, for any load increment, okay, delta P, delta Q, the software will give us the corresponding strain. That's all. Okay. So before using the software, modified CAMCLA model in your software, you need to get all these soil parameters, all these parameters. This is what we are going to do in this example. Okay. I will keep this question here, this stress strain relationship. So using these two equation, you remember this one, P and Q. Okay. This is the mean effective stress. Okay, the mean effective stress. This means we take the average of all the three principal stresses, the sigma 1 plus sigma 2 plus sigma 3 divided by 3, or considering that sigma 2 and sigma 3 are the same, then we can consider this one. And this is the sharing stress, sigma 1 minus sigma 3. Okay, we did these two in the previous videos. Please check. So using these two, we can easily use this relationship. You don't understand how we obtain this? It's very simple. I hope you remember this figure, Q and P. And I hope also you remember that the M is just this slope. And what is slope? Slope is just this Q. By considering P and Q, you can obtain the slope. You remember that this P is just this one, okay? And Q is just this one. So instead of P and Q, you can just write these two here. 1/3 of sigma 1, sigma prime 1 plus sigma 2, sigma prime 3. This here, okay? So M is just the slope of these two. Okay, you can obtain the M very easily by considering that in this, you can obtain this relationship. Yeah, so you can see that this one, if you want, you can just you can see that this 1/3 sigma 1 plus 2 sigma 3 is just the P here. Okay, and this one is, there is no modification at all, sigma 1 minus sigma 3. This is this one. So you can see that this is, M is just the slope. Yeah, this the slope of this critical line. Okay, so which means just Q divided by P, and you can obtain slope. This is just normal slope in mathematics. So if you understand, I hope you understand this equation. Okay, then we can move to, by using this, we can modify this a little bit to obtain something like that, which is will help us to correspond in a more column plot. Okay, the more column plot, this will be similar to the more columns. You can modify this equation to this one also very easily. So the more column is this one. You remember? More column. In this, you have sigma 3 here and you have sigma 1 here. Sigma 1 is the highest stress. Okay. So if you do, remember that this small column, this curve, this failure envelope of more column also is similar to the critical line. I hope you remember that this is same as critical line. So it means that once this circle touch the place where the circle touches the line is here, is failure. Okay, So if we take this circle, the radius of this circle here, from this point to the point where this will touch the circle will touch the failure envelope, we can see that this distance that I'm trying to draw here, from here to here, is the radius of this circle, right? So this radius of this circle is just like the diameter will be here, from here to here, means sigma 1 minus sigma 3, and I divide this by 2. It will give us the radius, okay? But anyway, if we want to get this angle, the phi here, cosinus or sinus of this angle will be what? The opposite side divided by this, okay? So this is the Moore Coulomb. As I said, the critical state line is equivalent to the failure envelope of this Moore Coulomb, okay? So we can write something like this. If I say what is the sinus of this this angle again? As I said, it's if we take this one from here to here, okay, and here, I think this is more Coulomb. In soil mechanics, maybe even 1 or 2. Soil mechanics 1, you have seen this relationship, okay? So now, if we check these two relationships, this one and this one, what is the difference? Don't you see that this is exactly same as this one by correspondence? Because sigma 1 minus sigma 3 here is sigma 1 minus sigma 3. So these are same, okay? Here, sigma 1 plus sigma 3, sigma 1 plus sigma 3, these are same. This means that all this is equal to this one. So we can write it here, okay? The sinus of this angle, which is here again, is given by this. So there is a relationship between the slope of this envelope, M, of the critical line, and this phi, sinus of phi, okay? So this is a good beginning for us. It will help us to determine all the other factors. And this is just the given data in our example, okay? Do you remember the Moore Coulomb friction? Phi is 20. This is just this angle here, okay? Which is our angle here, phi here. So it is given in the exercise, in the tutorial, in the example, okay? And we can, by replacing this 20 here, we can easily obtain the value of M, okay? Do you agree? And then the consolidation test, the slope of isotropic consolidation line is 0.3 and the recompression line is 0.05, and we have a void ratio 0.9. These two line, okay, the recompression line is this one, okay, compression line, and the normal consolidation line is this one. So the slope of this compression line is this one, and the slope of this normal line is like these two slopes are given here, 0.3 and 0.05. Okay, so we can say, as I said before, from this phi, which is 20, we can easily obtain the value of M. Okay, don't forget that we are looking for these parameters, all the parameters here in this D matrix. M is obtained already, 0.77. So we have 1 already, okay? Let's go for the others. From this equation, equation 15 is this equation, and also it given here 0.3, the alpha. This the slope here, consolidation line. Okay, the slope of consolidation line. It's here. It's given in the and even if it is not given, you have to do the isotropic consolidation test in the lab to obtain it. Please go back in the previous video and you will see what I am talking about. We even saw the apparatus to do this, to perform this isotropic consolidation test. Okay, please remember that even if it wasn't given here, you can still do this test. And also this value of this angle also, if it was not given, we can obtain it by doing plotting from triaxial test result. If you have sigma 1, sigma 3, we can plot this and obtain the angle and the cohesion. We can obtain this angle here. Okay, but it's given here. So we have then, let's come back, this alpha, or what is lambda, not alpha, lambda. And also we have this kappa here. Okay, this is kappa is given here as the slope of the recompression line. Yeah. Okay, so we have this lambda and we have kappa. Then we have also m. What left is v. P, we will check p also. We'll check v. We need the v now. Okay, and for v, since we have the void ratio, which is 0.9, v is just 1.1 plus the void ratio, so which is 1.9. So we have this v also. Okay, so we need this one and this one, p here, and then I think it will be done. So we will consider, because the soil sample was taken from 2.5 meter in the ground, depth of 2.5 meters. Okay, and we will consider the unit weight of the soil is 18 kilonewton per cubic meter. So since here we don't consider shear force and also shear force on the vertical and horizontal plane and no groundwater, so we can use this equation to obtain the P and Q. The meaning of this, please listen this very carefully. It means that the vertical stress, the soil sample was taken from this depth, 2.5. So vertical stress means the weight of the soil, vertical weight of the soil will be taken as sigma 1. Okay, and the horizontal stress by using this K naught. Do you remember the relationship between vertical and horizontal pressure? They are linked by K naught, by this K naught. Okay, and the formula for K naught is given here. We did this in the previous, I think, 2 videos before this one. Please check back this formula. Okay, we are considering normally consolidated clay, so the over consolidation ratio is 1. So replacing this by 1, and the phi, we have it here, it is 20. Okay, so anyway, since this is 1, we can neglect this. So using 1 minus sinus of 20, okay, we can obtain this value 0.66. And remember that K naught is the link between vertical stress and horizontal stress in case of in the underground. Okay. So then, as I said, Q, this shear stress can be obtained as formula sigma 1 minus sigma 3. The sigma 1 is the vertical stress, which is obtained by using just the weight of the soil above this level. It means the unit weight multiplied by this depth. It's very simple. Okay, so 2.5 multiplied by 18. And now we use this K naught to obtain the horizontal stress. And as I say, the horizontal stress will be considered as sigma 3 in this case. Okay, will be sigma 3. So sorry, emails. So the horizontal, the vertical, the relationship between uh, vertical stress and horizontal stress is in the field. I'm talking in terms of field, not in the in a in a in a triaxial lab test. Okay, in the field, relationship between horizontal and vertical stress is just this K naught. So horizontal stress is K naught multiplied by vertical stress. The vertical stress is this one. Unit weight multiplied by the depth. So multiplying this by K naught, we obtain the horizontal stress. And as I said, the horizontal stress will be standing for sigma 3, and the vertical stress will be standing as sigma 1. Okay, so we can obtain the shear stress easily by doing that as 15.3 kPa. And the P, if we have sigma 1 and sigma 3, obtaining P is simple. It's just 1/3 sigma 1 plus 2 times sigma 3. And then we can obtain it by this using also, you remember that sigma 1 is the vertical stress, sigma 2 is vertical stress, sigma 3 is vertical stress multiplied by K naught. Okay, and we can do this in this way. Obtain then P here. So if we have the P here, remember that this parameter, what is the name of this anyway, is just Q divided by P. Okay, then we can have this also here as 0.44. So that being said, I think we have everything we are looking for. We have the M, we have lambda, we have kappa, we have V, we have P. Everything is covered now. So by using then this equation, we just replace the values and we obtain everything. Okay. Okay, V is here. As you see, P is this. Okay. So you can check by yourself. Okay, check please by yourself. And then by calculating everything, we obtain this formula. So when you are going in your soft, you have to give the software all these parameters. And then you can obtain the modified CAM-CLAY. You can perform the test under modified CAM-CLAY model and obtain the strain corresponding to any stress. You see, the link is done. For any stress increment, the strain corresponding, the link is done. Then I think this example will help you to understand more this modified CAM-CLAY model. Okay, that will be all for this video and for this chapter as well. We have completed the chapter now, and I hope it was a very long chapter, And the next one maybe will be shorter and more interesting for you because it will be directly related to the application in the engineering. Okay, so we will stop here this video. Thank you very much for your time and see you soon.